Okay, guys, so welcome to the second review session. I brought some apples, so anyone who solves a problem gets an apple. Okay? That's how this works. If there are apples left, I'll bring them home so I can make an apple pie. I mean, you can have some more. That's fine. I get them from the UVM farm. They're like, we have an apple share, so they give me every week. So it's a good use of the apple. They're pretty good. So, who wants to try the first problem? It's a very hard problem, so don't worry if you don't get it right. Okay, so actually, the question is, it seems simple, right? It's like, are all the hydrogens in the same plane? Yes or no? Yeah. You wanna give it a try?
Basically, do you want to draw something or?
Write the answer first.
All right, so this one is going to be yes, and this one is no.
Okay, and now the question is why? Right? See if you can draw.
Because the double bonds are stable, right? So basically we got 4 carbons here.
Uh-huh.
And because of that, for example, let's say this is horizontal, right? Double bond, this is vertical double bond. And this again going to be horizontal. So there's 3 planes,
yes.
Right? So the initial and the last one going to be in the same station because it's trigonal planar. The 2 hydrogen atoms going to be in the same position as them.
Yes.
Versus one more in the next one.
Yes, so what I will do is I'll draw in the hydrogens, okay? So here the hydrogens look like this, okay? So I'm actually trying to see, let's turn it around. I'm trying to see how you drew it. So I'm going to redraw it.
Yeah.
So it's a little bit easier to see, okay, guys? Let's see, I'll redraw it. So we'll leave the 4 carbons. Right now we have the double bonds. I'll just draw them in. And now we're going to draw the orbitals. Remember, whenever we have double bonds, we have p orbitals, right, which are overlapping, kind of like this. Okay, 2 p orbitals, they're overlapping. So let's say the first one, if the hydrogens here are coming out of the plane, like this would be, sorry, that's ugly. This would be coming toward us, this hydrogen, and the other hydrogen is going into the plane, right, with these things. Then we can draw the pi orbital for the first one, okay, which looks like this. You guys see that? And so we have overlap, for example, here and here. By the way, this first problem I think is by far the hardest of the whole problem set. Okay, so here we go. Now, what's the hybridization on the first atom here? That's sp3, right? Because the steric number is, sp2. Been a long day. sp2, because the steric number is 3. What's the hybridization on the next carbon atom? So this guy. sp, exactly. So that means if it's sp, we have 2 sp orbitals, right? And these are making the sigma bonds, so they're linear. They're painting the one of the part of the double bond. This one and this one, they're the sp orbitals, okay? But now we have 2 p orbitals, and one of the p orbitals is already involved in this first double bond we drew. But now the question is, what's the geometry of the second p orbital? It's coming toward us, okay? And so what I'm going to do is I'm going to pick 2 different colors, like orange and light blue or something. And so I'm going to draw it kind of coming out of the board. So I'm going to do it like people do it in physics. So you see one of the lobes is coming out, and then the other one, like light blue, is kind of in the back here. You guys see that? So that's coming out and into the board. It's a little bit hard to draw, but that's the second p orbital. And so now you see this has to make a pi bond with the carbon now on the right. That means this carbon must also have a p orbital oriented like that. Does that make sense? Sorry, I'm coming down here. Okay, so we'll draw that in like this. So that's the p orbital on this carbon. You guys see that? And so we can draw the overlap. There's some overlap back here, right, for the pi bond, and some overlap over here in the front. Okay? You see how that pi bond is now rotated 90 degrees from the first one? Just because it's sp hybridized. And now we can go back. Now we have another p orbital, of course, in this carbon there, which is again in the plane of the board. Okay, so we'll have another one, and I'm going to do another color again. We can do like, what should we do? Maybe, what's the name of this color? This is like purple. Let's do a purple one, right? So we have a purple one, and we need something bluish or greenish. Let's do this one. Okay? So that makes another pi bond. See? Here is the overlap. And down here is the overlap. You guys see that? And now where are the hydrogens? Because you see this is again the last carbon here is again sp2 hybridized, right? So that means it must be trigonal planar. One of them is pointing here. The p orbital is in the plane. That means the hydrogens are like this. Oh, that's pretty cool. I draw here and look. It's a pretty cool feeling. So yeah, that's, you see. So now what it means is the hydrogens in the end. You see, these hydrogens here are all in one plane. And that's why we have the yes. You guys see that? But now if we introduce another, see this has just another unit. Then, yeah, then it's 90 degrees. So the way I'm going to do it, I'll see without redrawing the whole thing. I'm just going to draw another unit and copy it. Paste. Ooh. Okay. So that's what we're starting with, and I'm going to erase the ending. Let's see. I should have erased this before. Let me just erase this plane. Yeah, you guys can discuss if you want. That's fine. Let me just erase it. And we need to erase the yes as well. But it's easier than redrawing the whole thing. Okay, so here we go. Right up to here, it's all the same. So far, so good. Up to here, it's all the same. And now we just add another unit. Right, we add another unit here. Because this has 1, 2, 3, 4, 5. And now, now we have another p orbital. We'll make it in dark red, for instance. This is again coming toward us. Right, so we'll make it, hold on, we need a bluish like color. I don't know, I don't have any more colors here. Let's pick this one. Beautiful color. Okay. Sorry. Here we go. Right? You see that overlap? It's coming out of the plane toward us again. And now you see where the hydrogens are, because again this carbon here, the last one, is again trigonal planar, but now it's in the plane of the board. That means these hydrogens are now like this. Okay? So now you see the hydrogens here at the end, they're not in the same plane as the hydrogens here on the other side. It's twisted like this. Any questions? Yes, please.
So would the red and the purple pi bonds be interacting, and then like the orange and the like rusty red also be interacting, like across?
Yes, that's an absolutely great question. So the question is, are the red pi bonds and the purple pi bonds, for instance, interacting? Mm-hmm. Yes, I think they are. And yes. But this is beyond of what you need to know at this point for the course. Okay? But a very good question. So it's actually a conjugated pi system, but it's conjugated in like different dimensions. It's really cool. Okay? So we give you an apple, and then thank you for answering the question. Any other questions? Okay. So I'm not going to throw it all the way through the room, but let's go to the next question. Again, a few more things here about bonding, right? So which do you think is stronger, a pi bond or a sigma bond, and why? Yes. See, you can write it on the iPad. And I will try to explain it. The why is more important, right?
My answer is pretty short, so it may not be.
Okay. Yes.
Okay.
Perfect.
Awesome.
Shorter, and it's so it's shorter. That's right. That helps, but it's also a stronger overlap. Okay. And I'll show you. I'll draw you a picture just to illustrate it a little bit more. Thank you. Yeah. So let's see. I'll shrink your thing a little bit, just so it's not. So I can still draw a picture here. But I can't. Somehow I can't do anything here. Here we go. Okay. So sigma. Let's do sigma over here and pi over here. Right? Let's say we take carbon, carbon, right? So everything is the same. So we say we have a carbon, carbon sigma bond, right? That would, for example, be, you can use different orbitals to make it depending on what's the hybridization of the carbon. Let's say we use an sp3 hybridized structure, right? It's the sp3 hybridized carbon. So it would look something like this. You see you have a red part and another red part here. They're overlapping. Right? Remember, there's a big lobe, and the big lobes are pointing toward each other, and then the small lobe back here in blue. Okay? So that's our sigma bond. And you see the overlap, the overlapping portion here in the middle is pretty strongly overlapping, right? Now, let's look at the pi bond. So pi bond, again, we'll do carbon, carbon, and we'll have a sigma bond already to hold them together. And now we will have, this is pretty much a pi bond, right? Kind of like what we already had before. You see now the overlap is much weaker. That's why I have to like draw these. Originally they're not even overlapping. These p orbitals, they're kind of far apart from each other. You see that? Because the geometry is different. So that's why there's stronger overlap, and that's why the pi bond is weaker. Okay, any questions? Yes, please.
Would it also be true that the pi bond is stronger because it exists at like a lower energy level?
The sigma bond.
Yeah.
Not the pi bond. Yeah.
Sigma bond would
So
be-
yeah. So the question was: is it also true that the sigma bond is stronger because it's at a lower energy level? Because it's made out of, you mean, of lower energy orbitals?
Yeah.
That's not necessarily true. So in general, what one finds, the energy levels, they have an influence on the strength of a bond, but it's usually the closer together in energy two orbitals are, which form the bond, the stronger the bond. But you don't have to know that. That's like more advanced molecular orbital theory. So you can have two pretty high energy orbitals, and if they're both at equally high energy, they can make a pretty strong bond. Right? You can have at the same time you can have an orbital which is really low in energy interacting one with which is slightly higher, and they make a weaker bond. Right? So it's the overlap and how close they are in energy. Yes. Okay. Good question though. All right. So next question. Right. So then the question is, which would be longer, an sp3 sigma bond, or an sp? I think we don't need this overlap here. That just makes the question sound weird. So which is longer, an sp3 sigma bond, or an sp sigma bond, and why? Anybody wants to try? Who wants to try? That's a harder one. Don't worry if you don't get it right. We can discuss it. If I have to solve it, I will get that. You want to try? So, you want to try? Yeah, give it a try. Thank you. You get an apple regardless if you answer it correctly.
Does this make sense? Like I said, I don't know how to phrase it, but I was drawing it out this way.
Uh-huh.
Does that make sense? Because it's like longer here.
Yeah. So think about the following. Let's do it together. I think your argument makes sense.
Okay.
So that you can write while I'm talking.
Okay.
So think about the following. What matters for the length is how big the orbitals are initially, right? If you have smaller orbitals, for example, if you have two s orbitals, they will come together really closely. And if you have two p orbitals, they're bigger. They're further away from the nucleus, so then it makes a longer bond. So the question is really, what has more S character? Is it an sp orbital or is it an sp3 orbital? Sp, right? Because in an sp orbital, we are mixing one s orbital and one p orbital, so it has 50% S character. And so the sp orbital is closer to the nucleus. So it means it's a little smaller. The lobe is smaller. It's closer to the nucleus than for an sp3 orbital. Because in an sp3 orbital, it's much more like a p orbital. Right? It's like, what is it? 75% P, right, and 25% S in sp3. So then which bond is shorter? The sp bond, exactly, because it has more S characters, so the orbitals are smaller to start with, and so it makes a shorter bond to get the same overlap. Does that make sense? And so you kind of took notes for me. This is great.
Okay, so this kind of makes.
Recording. Okay, I'm sorry for people who are watching. Somehow the recording got paused after 15 minutes. Okay, that's the risk. Yeah, I don't know. We'll try. I don't know why it's paused. It's fine. It doesn't matter. Next time I will upload it. So next one. So we have two more problems, right? We want to. This one we just want the molecular formula. Who would like to do the molecular formula for this one? Okay. Yeah. So I will blame you guys. Somebody who drew on the iPad must have pressed the pause button.
I don't remember the order the atoms go in.
So the question is, what order do the atoms go in?
Is it C, H, O, and then the other ones?
It's C, H, and then alphabetical.
Okay.
That's the order. C, H, and then alphabetical. No, C, H, and then alphabetical. Oh, okay. And this is what I remember. Is that what the book says? Okay. Okay, thank you very much. Let me get you an apple. I think we still have some apples. C, H, and alphabetical. That's the last apple. I'm sorry. So the person who does the last, we have one more, right? Or two more, one more. The last problem, you won't get an apple. Is this correct? Is that what everybody got? Yeah. Because I didn't count. Okay, great. So last one, Tamiflu, right? That's the stuff. I think it's like an antiviral drug. We will do we want to just identify all the functional groups. Okay? So let me get you a purple thing. You want to change the color? You can just change it
You
here.
don't like purple? Oh, yeah.
You want red? Or what do you like?
I was very color-coded with
Oh, I see. Keep changing the color. I love that. Just pick different colors while you draw it. Okay?
Okay.
Thank you. Yeah, next time we'll just keep an eye on the recording. Oh, okay. So thank you. So you're doing methyl and stuff. That's kind of naming, but
Too much?
It's
You just want function.
too much.
Okay.
So for functional groups, what I want on an exam, give me the ones you have learned. Those we put in the table, in the video, those we talked about, the ones in the book.
Okay.
So the other things those are not really, for example, methyl is not really a functional group. It's just kind of, it's just a substituent. It's just like CH3. But then a CH3 is almost the same reactivity as a CH2, CH3. So it's too much. It's too fine-grained. So what I'm looking for is esters, amides, aromatic rings, right? Mm-hmm. Try not to give me alkyl chain as a, because there's always alkyl chains, okay?
Yeah.
Thank you. Let's see. So the amide is great, the amine is great, the ether is great.
I don't know if this one's an aromatic because it doesn't have
It's
confluence.
not.
Okay. Only if
not.
it's confluent.
So this is a good thing. So this is not an aromatic ring because that's very important. Why? Because an aromatic ring needs to have 3 double bonds. It needs to be conjugated all the way through. So every carbon, every atom in the aromatic ring has to have a double bond. At least with carbon. With hetero atoms, you can have different. It's complicated. And this is a carboxylic. So carboxylate is something you don't actually have to know. Carboxylate is this one. It's a negatively charged carboxylic acid. Okay. So what we want to call it, this is an ester. This is you can call it a carboxylate ester. But we have to put. But generally, all you have to put on an exam. It's just ester. Okay?
Okay.
Very good. And then there's one more because we took the aromatic ring out. When we took the aromatic ring out, now we have a double bond. So we could call this an alkene. Okay? So if it's not an aromatic ring, you have a double bond, you can call it an alkene. Okay, yes, please.
Do we have to label all alkenes on tests when asked for functional group? Like,
So the question is, do you...
part of something bigger?
Yes, so yeah. So the question is, do you have to label all the alkenes on a test? What I usually ask for on a test is I will give you a big molecule, something pretty, like, you know, like this thing, and I will ask you to label, let's say, 3 functional groups in the molecule. But you have to label 3 actual functional groups. So maybe I give you a molecule which just has an alkene, an amide, and an ester, and that's all it has. Then you have to label it as an alkene, otherwise you only find 2.
I imagine you can't just label a bunch of alkanes.
No, if you just label alkanes, I will not give you points. Yeah, you can't just label alkanes as kind of a functional group, but just like a pseudo-functional group. So don't just label alkanes. I will not give you points. I mean, you can, but it's not, okay? Real functional groups, right? Yes, one more question.
That it's just, is an amine just an N connected to any 3 things?
An amine?
Yeah, I mean.
Yes, an amine is connected to any trace except if it's an amide. For instance, you know, if it's connected to a carbon which then has a double bond to an oxygen, then it's an amide, then it's not an amine.
Okay.
But if it's connected to a hydrogen and three carbon atoms otherwise, or 3 ethyl groups or something, yeah, then it's an amine. Okay? Very good questions. Thank you, guys. Again, I'm sorry that this didn't completely record. If you have any friends, explain to them. We just you know, we paused the recording.
Number 9 before you switched it.
I will stop this one now. I think it's done.